Good afternoon, everyone. I'm sorry for being late. We have developed a set of tools for crash analysis of user level applications on ARM architecture. I'm going to talk about it. I have divided my talk into 5 main parts. Firstly, I will tell you why we started this work. And secondly, I will take a look at the related work. And thirdly, I will introduce our approach to build our tools. And then we'll see a little detail of implementation. And finally, I will finish my presentation with a brief summary. Before starting, I will simply introduce presenters first. I am Dongwoo Kim, and he is Sangwho Kim. We are students from South Korea. Our names look very similar to you, but we are not real brothers. Thank you. Let's get down to the business. We want to find remote code execution vulnerabilities of real-world Android apps. Our targets are apps that consume file data like Office file browser, and we are especially interested in native code that can make crash. So it's not a big deal to make targets get crashed by simple fuzzing. But the problem is that it's a very time-consuming task to analyze crashes to determine exploitability. Let's take a look at a crash sample. Here is the crash point. In order to determine exploitability, we need to find an instruction after crash point, which can change the program counter. In this case, if R2 register at the crash point is under control, we can manipulate the program counter to the shellcode. The next step is to figure out that the R2 register is affected by the user input. It is usually performed by a person manually, which takes a long time. So we needed something that can let us know whether the operand is affected by the user input in an automated manner. So we tried to take advantage of any tools for it, but unfortunately, there's nothing that we can use for our purpose in ARM architecture. So we have decided to build our own tools using taint analysis based on dynamic binary instrumentation. Our tools should be easy to use both on Android emulator and device. We want our tools to answer these questions. There are 2 related work. The first one is VDT. VDT was presented in 2009. This is for crash analysis of user level applications on Windows platform. It makes use of taint analysis. It works like this. At first, it makes trace log first, and then performs backward taint analysis. At the end, it tells whether the operand is affected by the user input or not. VDT consists of 2 parts, VDT tracer and VDT GUI. VDT tracer has been developed as an extension of WinDebug. It takes advantage of single-stepping of WinDebug for saving trace log into a file, including register context of each instruction. VDT GUI is a taint analysis program that takes in the trace log file and shows a list of executed instructions. And it allows the user to choose any operand of instruction to see it comes from the user input. If it turns out that the input data affects the operand, it shows the instruction chain that is engaged in the data transfer. The drawback of VDT is that a user has to manually figure out the memory address where the input data is loaded into and enter the memory range into the program in advance. Even though it is just a prototype for crash analysis of user-level applications on Windows platform, we were inspired by VDT, so we considered VDT as our role model. The next related work is Tree. It was presented in 2013, and this is also for crash analysis of user level applications. The principle of operation is almost the same with VDT, but they claim that it can support various architectures. Tree is a plugin of IDA Pro. So it is entirely based on the IDA, and since IDA has a capability of single stepping on various architectures, Tree just takes advantage of debugging features of WinDebug. Not WinDebug, IDA. It takes advantage of single stepping of IDA. But IDA cannot provide stable instruction tracing in multi-threaded environments on ARM architecture. So Tree has a limitation to apply to real targets. Since there are no appropriate tools for instruction tracing in ARM architecture, we intended to build a DBI tool on the scratch. There are two types of DBI. The left one works on the same context of the target program. It can provide relatively fast instrumentations, but it's not appropriate for crash analysis because it may produce unexpected results in case of memory access violation. On the other hand, the right one can preserve the target context. So even though it has a high overhead, it's appropriate for crash analysis. So our choice is the right one. Here is the overview of our tools. Our tools consist of two parts, ARM Tracer and ARM Analyzer. Their roles are exactly the same with VDT of Intel architecture. But there are some challenges in instruction tracing. Because ARM does not provide hardware support for single stepping, whereas Intel does it, known for trap flag. So we have implemented it with DBM, that stands for debug breakpoints mechanism. It requires various considerations which are not necessary in Intel architecture, such as calculating next PC and handling signals in multi-threaded environments and handling instruction sequence for atomic operation. They will be explained later. In case of ARM Analyzer, it's not a simple job to identify semantics of ARM instructions and distinguish their syntax in terms of data propagation. And seeing the instruction set is very annoying because it handles multiple data with one single instruction, and it has its own register bank. Okay, I will see a little detail of implementation of ARM Tracer first. As I mentioned, we used DBM for instruction tracing in ARM architecture. It replaces an original instruction of the target program with breakpoint instruction at runtime in order to make exception. Right after the exception occurs, ARM Tracer can take control of the target process. Yeah. To do this, we have to determine the next PC. Yeah, step one. We have to determine the next PC to set the breakpoint by analyzing the current instruction. Once the next PC is determined, we need to save the instruction at the next PC before replacing it with the breakpoint, and then continue the targets. When the target hits the breakpoint, we have to restore the instruction, and then restore the instruction, and then determine the next PC to set a breakpoint again. This is repeatedly performed. But the important thing is that the breakpoint instruction should be different according to the instruction states. As you may know, there are two types of instruction states in ARM architecture, ARM states and thumb states. They have a different instruction size. So if we do not set the proper breakpoints according to the states, it will spoil the target context. So we have to be careful of the state change, which is called interworking. The interworking can happen by BX and BLX instructions only. When we determine the next PC, in most cases, we can just increase 2 or 4 bytes according to the states. But there are some instructions that can directly change the program counter. So we have to identify opcode and operand in case of these instructions. In addition, we have to address the interference by other threads. Since every thread shares code section, other threads also hit the breakpoint that is set only for the target thread. Yeah. So we have to carefully handle the signals caused by breakpoints to guarantee all the threads run properly. Otherwise, we may lose control of the target. There is one more problem caused by DBM. This is about instruction sequence for atomic operation. ARM does not provide single atomic instruction. Instead, it provides instruction sequence for it. So, but the important thing is that the sequence, if the sequence is intervened by DBM, it may cause infinite loop. So we have to identify the while single stepping, we have to identify the sequence and handle it. Now we are ready to perform the instruction tracing in ARM architecture. We can start tracing from the good point where the input file is loaded here. And we don't need the previous log for the analysis. At this point, we designate a specific thread as a target thread, which opens input file. Which opens the input file. And in addition, we can automatically figure out the memory address which where the input file is loaded by checking open and read functions. When we save the context of each instruction, we have to filter out instructions that are not executed because they can mess up tracking data propagation at ARM analyzer. I'm sorry. Unlike Intel architecture, all the ARM state instructions have condition flags. So the instruction is always fetched and executed. If it does not meet the specified condition of CPSR, the instruction is replaced by processor with the no operation code before being executed. So we have to compare the condition flags between instruction and CPSR before saving. And in general, the thumb state instructions have no condition flags, but there is an exceptional case. IT instruction of thumb to instruction set provides conditional execution. The principle of operation is different from the ARM state instruction, but anyway, we also have to filter out instructions that are not executed in IT block. Now, I will introduce ARM analyzer briefly. Here is the trace entry format generated by ARM tracer, and ARM analyzer parses each entry. It identifies instruction syntax based on the disassembly. For disassembling, we make use of Capstone, which is a lightweight disassembly framework. And ARM analyzer identifies objects in operands like register and memory address. We have classified instructions in terms of data propagation based on reference manual. As a result, we selected 77 instructions as our targets out of 117. So we implemented all the syntax of target instructions, and we also implemented some themed instructions as well. This is a view for user. Assume that the last instruction is the crash point. When a user chooses R3 register of source to see it comes from the input data, it works like this inside of ARM Analyzer. It finds, it backwards looks for an instruction that has R3 register as destination. So it will find this one, and it includes the source objects of the instruction. And then it will find R1 and effective address backwards again and again and again until the search finishes. So even though our tools are not yet complete, we performed an experiment to see how useful it is. So we generated crashes, many crashes against the Polaris Office, which is widely used on Android for document file browsing. We chose 7 crashes that look very interesting like this. If we have a control of R3 register, we can finally manipulate the program counter and flow, execution flow. We can change the execution flow. So we put them into our tools. At first, we tried to get trace logs with ARM tracer. We stopped tracing if it executes over 10 million instructions. So we got 4 of them. On average, it executes 7 million instructions, and it takes about 25 minutes respectively. We analyzed the 4 trace logs with ARM Analyzer. As a result, we found 2 exploitable crashes. The result came out within 15 seconds in the fast mode. The fast mode means it includes effective address only of source. On the other hand, normal mode takes a lot of time. I think we need to improve the performance. So it's a demo time. He's going to show a demo.
Okay, I'll show you on tracer first. This is target app. This is crash sample. We'll get a trace log file with ARM tracer. We give PID of the target app process and a part of name, the input file name as an argument. Logging. ARM tracer captured the input data. We cut down recording files because of the time limitation. Originally, it takes about 25 minutes. It shows that the number of the executed instructions is about 7 million, and the trace log file size is about 1 gigabyte. Now, I'll show you how to analyze to trace log file with ARM Analyzer. We're open to the trace log file. Yeah, drag and drop. Okay, loading. Here is crash point. we will see the crash points in IDA. Here's the crash point, and then here's the branch instruction. Please remember the R3. Searching now. We got the result. Here's an offset, the offset in the info file. Here's the instruction chain. This is input data range. We'll check. It really comes from the offset in the input data. Let's modify the data at the offset. Here's the offset. I will change it. It's double 3, double 2, double 1, double O. Sure. And now we'll get the trace through crash information with the caused by modified file. Modified file name is input crash new. Okay.
Locate clear.
Okay. Get the crash log file. And let's check out the R3 register value. Okay. This target app, crash log, R3. Here is, as you can see, this data that I modified in the file. Yeah. Okay, that's it.
Which means we can manipulate the program counter to the shellcode.
Okay.
Okay, I will conclude my talk. We have developed a set of tools for crash analysis of user-level applications on ARM architecture. We tested it with a real-world Android app on device, and as a result, we found 2 exploitable crashes. Before long, we are going to release our tools with source code. After some revisions, actually, there are some tricky bugs. So please participate in improving our tools. That's all about my presentation. And do you have any questions? Actually, I prefer to be asked personally. I'm a shy guy. Thank you.